Good morning. Welcome to today's session. Yesterday I have explained about NC coordinate system, floating zero and fixed zero, incremental versus absolute dimensioning system, and open loop control system and closed loop control system. So to program the NC processing equipment, it is necessary to establish a standard access system by which the relative positions of the tool with respect to the work can be specified. Coordinate system in NC using an NC drill press as an example. The drill spindle is in fixed horizontal position and the table is moved relative to the spindle. However, to make things easier for the part programmer, the viewpoint is adopted that the workpiece is stationary while the tool is moved relative to it. Accordingly, the numerical control coordinate system is defined with respect to the machine tool table. Two axes x and y are defined in the plane of the table. The z-axis is perpendicular to this plane, and movement in the z direction is controlled by the vertical motion of the spindle. The positive and negative directions of the motion of tool related to the table. So these are the shown in the figure. NC drill presses are classified as either 2-axis or 3-axis machines, depending on whether or not they have the capability to control the z-axis. A numerical control milling machine and similar machine tools like boring mill use an axis system similar to that of the drill press. However, in addition to the 3 linear axes, these machines may possess the capacity to control one or more rotational axes. 3 rotational axes indicated with the symbols. So indicated with the symbols A, B, and C. So this will represent the rotational axis. These axes are used to specify angles about the x, y, and z axis, respectively. To distinguish positive from negative angular motions, the right hand rule can be used. For turning operations, 2 axes are normally that all are required to command the movement of the tool related to the rotating workpiece. The z-axis is the axis of rotation of the work part, and the x-axis defines the radial location of the cutting tool. So this is about the axis. Next one, fixed zero versus floating zero. The purpose of the coordinate system is to provide a means of locating the tool in relation to the workpiece. Depending on the type of the NC machine, the part programmer may have several options for specifying the location. One of these options depends on whether the machine has a fixed zero or a floating zero. In the case of fixed zero, the origin is always located at the same position on the machine table. Usually the position is the southwest corner, lower left hand corner of the table, and all the locations must be defined by positive x and y coordinates related to that fixed origin. The second and more common feature on modern NC machines allows the machine operator to set the 0 point at any position on the machine table. This feature is called the floating zero. The part programmer is the one who decides where the 0 point should be located. The decision is based on part programming convenience. For example, the work part may be symmetrical and the 0 point should be established at the center of symmetry. The location of the 0 point is communicated to the machine operator. At the beginning of the job, the operator moves the tool under manual control to some target point on the table. So the target point is some convenient place on the workpiece or the table for the operator to position the tool. For example, it might be a pre-drilled hole in the workpiece. The target point has been referenced to the 0 point by the part programmer. So next one, absolute versus incremental positioning system. Another option sometimes available to the part programmer is to use either an absolute system of tool positioning or incremental system. Observed positioning means that the tool locations are always defined in relation to the 0 point. If a hole is drilled at a spot that is 8 inches above the x-axis and 6 inches to the right of the y-axis, the coordinate location of the hole would be specified as x equal to 6 and y equal to 8. By contrast, incremental positioning means that the next tool position must be defined with reference to the previous tool location. If in the previous drilling example, the previous hole had been drilled at an observed position of x equal plus 4 and y equal plus 5, the incremental position instruction would be specified as x equal plus 2 and y equal plus 3 in order to move the drill to the desired spot. So this is about the incremental system versus observed system. Next, I have explained about control systems in the NC machines, that is open loop control system and the closed loop control system. So open loop refers to a system where the communication between the controller system and the motor is one way. It is a simple type of loop system. After the user decides what he or she wants to do and generates some kind of code or some sort of work file, the NC software then creates the necessary step and direction signals to perform the desired task. Open loop system uses stepper motors. However, just because the system uses stepper motors does not mean the system is an open loop system. Stepper motors may be outfitted with encoders to provide position feedback just like servo motors. Stepper motors are able to operate in an open loop system while servo motors are not. Because stepper motors do not require feedback hardware and the price of an open loop system is much cheaper and simpler than a closed loop system. So drawback of the open loop system is because there is no feedback to the controller. If the motor does not operate as instructed, there is no way for the system to know. The controller system will continue performing the next task as if there is no problem until a limit switch is tripped or the operator resets the machine. Next one, closed loop system. The closed loop system has a feedback system to monitor the output of the motors. Closed systems are also able to correct errors in position, velocity and acceleration and also fault the system if the error is too large. Most of the closed loop controllers are PID or proportional integral derivative controllers. The encoder output is fed into the motor driver. A PID controller attempts to correct the error between a measured variable and a desired set point by calculating and then outputting corrective action that can adjust the process accordingly and rapidly to keep the error minimal. So the disadvantages of the closed loop system are cost and complexity. And today's session objectives are, so in today's session we will learn about manufacturing methodology and NC system and NC motion control system. NC manufacturing methodology. The steps which are followed in NC manufacturing are process planning, part programming, tape preparation, tape verification, and finally production. So these are the various steps involved in manufacturing methodology. So these are process planning, part programming, tape preparation, tape verification, and production. First one, process planning. In this, the engineering drawing of the work part must be interpreted in terms of the manufacturing processes to be used. This is called process planning. In this, a route sheet is prepared. A route sheet is a listing of the sequence of operations which are performed on the work part. It also lists the machines through which the part must be routed in order to perform according to sequence of operations. So what is route sheet? A document accounting for the output of production and tracing the sequence of operations of a batch of manufactured components. The route sheet is used in serial and especially individual production to show the workers' output. Calculate the wages of the workers and exercise operative supervision of the movement of the work parts in production. The route sheet accompanies the batch of components in all manufacturing operations to aid in supervising the observance of technological discipline and the preservation of all elements. And in the process planning, we can define route sheet as it is a document providing information and instructions for converting the raw material into the finished parts or products. It defines each step of the production operation and lays down the precise path or route through which the product will flow during the conversion process. Route sheet contains the following information. Those are the operations required and their desired sequence, machine or equipment to be used for each operation, estimated setup time and operation time per piece, tools, jigs and fixtures required for the operation, detailed drawing of parts, sub-assemblies and final assemblies, specifications, dimensions, tolerances, surface finishes and quality standards to be achieved, specification of raw material to be used, speed, feed, etc. to be used on the machine tools for the operations to be carried on, inspection procedure and metrology tools required for inspection, packaging and handling instructions during the movement of parts and sub-assemblies through the operation stages. I'll explain about process planning once again. In this, the engineering drawing of the work part must be interpreted in terms of the manufacturing processes to be used. This is called process planning. In this, a route sheet is prepared. A route sheet is a listing of the sequences of operations which are performed on the work part. It also lists the machines through which the part must be routed in order to perform according to sequence of the operations. Sorry, this is the route sheet. So this is about the process planning. The next step of manufacturing methodology on any system is part programming. Part programming is the process of making NC instructions. It can be done either manually or computer assisted. So manual part programming. In manual part programming, the part programmer specifies the machining instructions on a form called a manuscript. Manuscripts comes in various forms depending on the machine tool and tape format to be used. For example, the manuscript form for a 2-axis point-to-point drilling machine would be different than one for a 3-axis countering machine. As mentioned, the manuscript is a listing of the relative tool and workpiece locations. It also includes other data such as preparatory commands, miscellaneous instructions, and speeder feed specifications, all of which are needed to operate the machine under tape control. The manuscript is designed so that the NC tape can be typed directly from it on a flexowriter or similar tape punch device. We shall divide manual programming jobs into two categories: point-to-point jobs and countering jobs. Except for complex work parts with many holes to be drilled, manual programming is ideally suited for point-to-point applications. On the other hand, except for the simplest milling and turning jobs, manual programming can become quite time consuming for applications requiring continuous path control of the tool. Accordingly, we shall only concern ourselves with manual part programming for point-to-point operations in this chapter. Manual counter programming requires such tedious and detailed calculations that the space needed for the topic countering is much more appropriate for computer-assisted part programming. I'll explain about manual part programming once again. The programmer first prepares the program manuscript in a standard format. Manuscripts are typed with a device known as Flexowriter, which is also used to type the program instructions. After the program is typed, the puncher tape is prepared on the Flexowriter. Complex shaped components require tedious calculations. This type of programming is carried out for simple machining parts produced on point-to-point machine tool. To be able to create a part program manually, need the following information: knowledge about various manufacturing processes and machines, sequence of the operations to be performed for a given component, knowledge of the selection of cutting parameters, editing the part program according to the design changes, knowledge about the codes and functions used in the part program. So next one, computer assisted or computer-aided part programming. If the complex shaped components requires calculations to produce the components are done by the programming software contained in the computer. The programmer communicates with this system through the system language, which is based on words. There are various programming languages developed in the recent past, such as APT, Automatically Programmed Tools, ADAPT, Autospark, Combat2, 2CL, Split. Is used for writing a computer program, which has English-like statements. A translator known as compiler program is used to translate it in form of acceptable to MCU. The programmer has to do only following things: define the work part geometry, defining the repetition work, specifying the operation sequence. Over the past years, a lot of effort is devoted to automate the part program generation with the development of the CAD or CAM system. Interactive graphics system is integrated with the NC part programming. Graphics-based software using menu-driven technique improves the user friendliness. The part programmer can create the geometrical model of the CAM package or directly extract the geometrical model from the CAD/CAM database. Built-in tool motion commands can assist the part programmer to calculate the tool paths automatically. The programmer can verify the tool paths through the graphic display using the animation function of the CAM system. It greatly enhances the speed and accuracy in the toolpath generation. So I'll explain about part program once again. The part program is a sequence of instructions which describe the work which has to be done on part in form required by computer under the control of numerical control computer program. It is the task of preparing a program sheet from a drawing sheet. All data is fed into the numerical control system using a standardized format. Programming is where all the machining data are compiled and where the data are translated into a language which can be understood by the control system of the machine tool. The machining data is as follows: machining sequence, classification of processes, tool startup point, cutting depth, tool path, etc. Cutting conditions, spindle speed, feed rate, coolant, etc. Selection of the cutting tool. While preparing a part program, need to perform the following steps. First one, determine the startup procedure, which includes the extraction of dimensional data from the part drawings and data regarding surface quality requirements on the machine component. Select the tool and determine the tool offset. Set up the zero position for the workpiece. Select the speed and rotation of the spindle. Set up the tool motions according to the profile required. Return the cutting tool to the reference point after the completion of work. End the program by stopping the spindle and coolant. The part programming contains the list of coordinate values along the X, Y, and Z directions of the entire tool path to finish the component. The program should also contain information such as feed and speed. Each of the necessary instructions for a particular operation given in the part programming is known as NC word. A group of such NC words constitutes a simple NC instructions known as block. The methods of part programming can be of two types depending upon the two techniques as below. So this one, manual and computer assisted. So manual part programming, the programmer first prepares the program manuscript in a standard format. Manuscripts are typed in with a device known as flexowriter, which is also used to type the program instructions. After the program is typed, the punch tape is prepared on the flexowriter. Complex shaped components require tedious calculations. This type of programming is carried out for simple machining parts produced on point-to-point machine tool. To be able to create the part program manually, need the following information. First one, knowledge about the various manufacturing process and machines. Second one, sequence of operations to be performed for a given component. Third one, knowledge of the selection of cutting parameters. Fourth one, editing the part program according to the design changes. And finally, knowledge about the codes, functions, and used in part programs. Next one, computer assisted part programming. If the complex shaped components require calculations to produce the components are done by the programming software contained in the computer. The programmer communicates with this system through the system language, which is based on words. These are various programming languages developed in the recent past, such as APT, ADAPT, AutoSpot compared to 2CL Split is used for writing a computer program which has English-like statements. Translator known as compiler program is used to translate it in a form of acceptable to MCU. The programmer has to do only following steps: define the work part geometry, defining the repetition of work, specify the operation sequence. So this is about the part program. To conclude the part programming as follows. In this step, a part programmer plans the process to be done by numerical control. A part programmer is one who prepares the part program. He is responsible for planning the sequence of machining operations to be done by numerical control. Next part is tape preparation. So the tape preparation, except for the physical form of coding, that is punched holes, many of our comments on the programmer formatting and coding apply equally well to other forms of input media such as magnetic tapes. The NC tape, the punched tape used for the NC is 1 inch wide. So this example of puncture tape. It is standardized as shown in this figure. So puncture tape, which has been responsible for many of the important standards in the NC industry, the tape can be made out of several materials. Paper tape is common, although its cost is low. It is not durable and therefore not appropriate for repeated use. Stronger tape materials suitable for higher production use include mylar reinforced paper, mylar coated aluminum, and certain plastics. Paper is often used for the initial preparation and testing of the part program. Then a production tape is duplicated out of one of the more durable materials for shop floor use. The puncture tape paper is returned as the master copy. Holes are punched in the tape using a tape punch machine like flexowriter. Tape preparation is accomplished either manually or using the computer. In the manual method, the tape punch machine operates in conjunction with the typewriter-like machine, early versions of which were called flexowriters. Each character typed on the flexowriter is converted to a set of hole patterns in the punched tape. With the computer method, the tape punch machine is controlled by the computer according to high-level instructions that have been prepared by the part programmer. The end result with either manual or the computer method is the same. A puncture tape representing commands to operate the NC machine. There are 8 regular columns of holes running in the lengthwise direction of the paper. There is also a 9th column of holes between the 3rd and 4th regular columns. However, these are smaller and are used as sprocket holes for feeding the tape. So this figure, there are 8 regular columns of holes running in the lengthwise direction of the tape. So this figure represents nearly every position of the tape. However, the coding of the tape is provided by either the presence or absence of a hole in the various positions. Because there are 2 possible conditions for each position, either the presence or absence of the hole, this coding system is called a binary code. It uses the base 2 number system, which can represent any number in the form more familiar base 10 or decimal system. In the binary system, there are only 2 numbers, 0 and 1. The meaning of successive digits in the binary systems is based on the number 2 raised to successive powers. The first digit is 2 to the power of 0, like this, 2 to the power of 0, 2 to the power of 1, so up to 2 to the, so like this. The 2 numbers 0 and 1 in the successive digit positions indicate either the presence or absence of the value. For example, the decimal number 5 is represented in the binary system by 0101. The conversion from the binary to decimal system makes the use of the following computation. For example, 5 represented with 0101. And in the binary system, 4 digits are required to represent any of the single digit number in the decimal system. Here there are 8 regular columns of holes in the standard NC punched tape. The reason 8 columns are needed on the tape is because there are other symbols that must be coded on the tape besides numbers. Alphabetical letters, plus and minus signs, and other symbols are also needed in NC tape coding. 8 columns provide more than enough binary digits to define any of required symbols. In fact, the fifth column position is used exclusively as a check called parity on the correctness of the tape. The way the parity check works is this: the NC tape reader is designed to read an odd number of holes across the width of the tape. Whenever the particular number or symbol being punched calls for an even number of holes, an extra hole is punched in the column fifth, hence making the total an odd numbers. For example, the decimal number 5 uses the punched hole in the columns 1 and 3, an even number of holes. Therefore, a parity hole would be added. The decimal number 7 already uses the odd number of holes, columns 1, 2 and 3. So parity hole is not needed. The parity check can helps to assure that the tape punch mechanism has performed a complete hole in all required positions. If the tape reader counts an even number of holes in the tape, it would signal the operator that a parity error had occurred. A binary digit is called a bit. It has a value of 0 or 1 depending upon the absence or presence of the hole in a certain row or column position on the tape. Out of a row of bits, a character is made. A character is a combination of bits which represents a letter, number, or other symbol. A word is a collection of characters used to form part of an instruction. Typical NC words are exposition, byposition, cutting speed, and so on. Out of a collection of words, a block is formed. A block of words is a complete NC instructions. Using an NC drilling operations as an example, a block might contain information on the x and y coordinates of the whole location. The speed and feed at which the cut should be run, and perhaps even a specification of the cutting tool. To separate blocks, an end of block symbol is used. The tape reader feeds the data from the tape into the buffer in blocks. That is, it reads in a complete instructions at a time. NC word. Following is a list of the different types of words used in the formation of a block. Not every NC machine uses all the words. Also, the manner in which the words are expressed will differ between machines. By convention, the words in a block are given in the following order. First one, sequence number N words, G words, coordinates X and Y, Z, X, Y, Z words. These give the coordinate position of the tool. In a 2-axis system, only 2 of the words would be used. In a 4 or 5-axis machine, additional A words, B words would be specified the angular positions. Although different NC systems use different formats for expressing a coordinate. For example, X 7.235, Y 0.5. Some formats do not use the decimal point in writing the coordinate. The plus sign to decline a positive coordinate location is optional. The negative sign is of course mandatory. So feed rate, efforts, cutting speed. They specify the cutting speed of the process, the rate at which the spindle rotates. Units are revolutions per minute. In a machining operation, it is usually desirable for the tool engineer to specify the speed in terms of the relative surface speed of the tool and work. Tool selection, this part would only be needed for machines with a tool turret or automatic tool changer. Miscellaneous functions, etc. Tape format. The organization of words within blocks is called the tape format. three tape formats: word address format, tab sequential format, fixed block format. The tape format refers to the method of writing the words in a block of instructions. Within each format, there are variations because of differences in machining process, type of machine, features of the machine tool, and so on. So in the word address format, a letter precedes each word and is used to identify the word type and to address the data to a particular location in the controller unit. The X prefix identifies the X coordinate word, S prefix identifies the spindle speed, and so on. Tab sequential format. This tape format derives its name from the fact that the words are listed in a fixed sequence and separated by depressing the tab key when the typing manuscript on a flexowriter. Fixed block format. This is the least flexible and probably the least desirable of three formats. Not only must the words in each block be in identical sequence, but the characters within each word must be the same length and format. If a word remains the same from block to block, it must nevertheless be represented in each blocks. So this is about the tape preparation. So to conclude this, in manual part programming, the punched tape is prepared from the part program manuscript on a typewriter-like device like flexowriter provided with tape punching facility. In computer-assisted part programming, the computer interprets the list of part programming instructions. It performs necessary calculations to convert this into a set of machine tool, motion commands, and then controls a tape punch device to prepare the tape for the NC machine. So before going to the next topic, I'll explain about the dimension of the taping. Tape for punching was 0.1 mm thick, and two most common widths are 11 by 16 inch for 5-bit code and 1 inch for tapes with 6 or more bits. Hole spacing was 0.1 inch in both directions. Data holes were 0.072 inches in diameter. Feed holes were 0.046 inches. I'll explain about the dimensions once again. Tape for punching was 0.00394 inches or 0.1 mm thick. The two most common widths were 11 by 16 inches for 5-bit code and 1 inch for tapes with 6 or more bits. Hole spacing was 0.1 inch in both directions. Data holes were 0.072 inches in diameter. Feed holes were 0.046 inches. The limitations of the paper tape were reliability. It was common practice to follow each mechanical copying of a tape with a manual hole-by-hole comparison. Rewinding the tape was difficult to prone to problems. Great care was needed to avoid tearing the tape. Some systems used fan-fold paper tape rather than rolled paper tape. In these systems, no rewinding was necessary, nor were any fancy supply reel, take-up reel, or tension or mechanisms required. Low information density. Datasets much larger than a few dozen kilobytes are impractical to handle in paper tape format. So these are the various limitations of the paper tape. And advantages, some of the advantages are longevity. Although many magnetic tapes have deteriorated over time to the point that the data on them has been irretrievably lost, punched tape can be read many decades later if acid-free paper or mylar film is used. Some paper can degrade rapidly, of course. Human accessibility. The whole patterns can be decoded visually if necessary, and torn tape can be repaired. Editing text on punched tape was achieved by literally cutting and pasting the tape with scissors, glue, and by taping over a section to cover all holes and making new holes using a manual hole punch. Magnetic field immunity. In a machine shop full of powerful electric motors, The numerical control programs need to survive the magnetic fields generated by those motors. Easy of destruction. In the case of cryptographic keys, the inherent flammability of paper tape was an asset. Once the key had been loaded into the device, the paper tape could simply be burned, preventing the key from falling into other hands. So these are the various advantages of using paper tape. Next one, tape verification. In manual part programming, tape verification, in this step the puncture tape is checked for accuracy. A foam or plastic material is used to make the part and a machine tool using this tape. Any error on the tape will result in the same error on the job. The puncture tape is modified. It may require 3 attempts before the tape is correct and ready to use. So I'll explain about once again about the tape verification. In this step, the puncture tape is checked for the accuracy. A foam or plastic material is used to make the part on a machine tool using this tape. Any error on the tape will result in the same error on the job. Then we have to modify the puncture tape. And the next step is production. This is the final step. The final step in the NC manufacturing is to use the NC tape in production. In this, NC machine tool is prepared for machining a workpiece. The operator's function during the production is to load the raw material in the machine tool and then bring the cutting tool to the standard starting position related to the workpiece. When the machine is started, the machining is performed on the workpiece according to the instructions on the tape. When the machining is completed, the operator removes the workpiece from the machine and loads the next workpiece. So this is about the production. I'll explain about the production once again. This is the final step in NC manufacturing. In this, NC machine tool is prepared for machining a workpiece. The operator's function during the production is to load the raw material in the machine tool and then bring the cutting tool to the starting position related to the workpiece. When the machine is started, machining is performed on workpiece according to the instructions on the tape. When the machining is completed, the operator removes the workpiece from the machine and loads the next workpiece. So this is about the NC manufacturing methodology. The steps in the NC manufacturing methodology are process planning, part programming, tape preparation, tape verification, and production. Next topic, NC motion control system. Positioning control system. In order to accomplish the machining process, the cutting tool and workpiece must be moved relative to each other. In NC, there are 3 basic type of motion control system. Those are point-to-point, straight cut, and contouring or continuous path. First one, point-to-point. It is sometimes called positioning system. In PTP, the objective of the machine tool control system is to move the cutting tool to a predefined location. The principal function of the PTP is to position the tool from one point to another within the coordinate system. The positioning may be linear in the XY plane or linear and rotary if the machine has a rotary table. Each tool axis is controlled independently. Therefore, the programmed motion always in rapid traverse. Once the tool reaches the desired location, the machining operation is performed at that position. NC drill presses are a good example of PTP systems. The spindle must first be positioned at a particular location of the workpiece. This is done under PTP control. Then the drilling of the hole is performed at the location and so forth. Since the no cutting is performed between holes, there is no need for controlling the relative motion of the tool and workpiece between hole locations. PTP systems are the simplest machine tool control systems and are therefore least expensive of the three types. However, for certain processes such as drilling operations, tapping, riveting and spot welding, PTP is perfectly suited to the task and any higher level of control would be unnecessary. So this is a point-to-point control system. I'll explain once again about it. PTP is also sometimes called positioning system. In point-to-point positioning, the objective of the machine tool control system is to move the cutting tool to a predefined location. The principal function of the PTP is to position the tool from one point to another within the coordinate system. The positioning may be the linear in XY plane or linear and rotary in the machine has a rotary table. Each tool axis is controlled independently and therefore programmed motion always in rapid traverse. Once the tool reaches the desired location, the machining operation is performed at that position. So NC drill presses are common good example for PTP system. The spindle must first be positioned at a particular location on the workpiece. This is done under PTP control. Then the drilling of the hole is performed at that location and so forth. Since no cutting is performed between the holes, there is no need for controlling the relative motion of the tool and workpiece between the hole locations. Positioning systems are the simplest machine tool control systems and are therefore least expensive of the three types. However, for certain processes such as drilling operations, tapping and riveting and spot welding, PTP is perfectly suited to the task and any higher level of control would be unnecessary. Next one, straight cut. Straight cut control systems are capable of moving the cutting tool parallel to one of the major axes at a control rate suitable for machining. It is therefore appropriate for performing milling operations to fabricate workpieces of rectangular configurations. Most of the straight cut systems can fitted with manually adjustable feed control. This feed control is shared by all the programmable axes of the NC machine. Because of this shared feed control feature, the system can also perform milling operations at 45 degrees to the primary axis of the machine. Example of the straight cut is shown in this figure, and this is the animation. I'll explain once again about straight cut positioning control. Straight cut control systems are capable of moving the cutting tool parallel to one of the major axes at a control rate suitable for machining. It is therefore appropriate for performing milling operations to fabricate workpieces of rectangular configurations. Most of the straight cut systems are fitted with manually adjustable feed control. This feed control is shared by all the program axes of the NC machine. So next one, countering or continuous path NC system. Countering is the most complex, the most flexible and the most expensive type of machining tools control. It is capable of performing both PTP and straight cut operations. In addition, the distinguishing feature of the countering NC system is their capacity for simultaneous control of more than one axis movement of the machine tool. The path of cutter is continuously controlled to generate the desired geometry of the workpiece. Countering system generates continuously controlled tool path by the capability of computing the points of the path called interpolating. For this reason, the countering systems are also called continuous path NC systems. All NC countering systems have the ability to perform linear and circular or parabolic interpolation features which recorded in the NC computer. So these are examples. So this is a contouring. I'll explain about contouring once again. It is the most complex and the most flexible and the most expensive type of machine tool control. It is capable of performing both PTP and straight cut operations. In addition, the distinguishing feature of contouring NC system is the capacity for simultaneous control of more than one axis movement of the machine tool. The path of the cutter is continuously controlled to generate the desired geometry of the workpiece. Contouring systems generates a continuously controlled tool path by the capability of computing the points on the path, interpolating. For this reason, contouring systems are also called continuous path NC systems. All NC contouring systems have the ability to perform linear and circular or parabolic interpolation features. So this is the contouring animation. In this session, we have learned about manufacturing methodology, steps in manufacturing methodology. Those steps are process planning, part programming, tape preparation, tape verification, production. In NC control system, those are PTP point-to-point control system, straight cut, and continuous path contouring type system. Thank you.